Hello everyone, welcome to the lecture again. Today we are going to study the variable mass problem. So herein we have a system which is either gaining the mass or losing the mass. Let us consider a system which is gaining the mass. So we are going to derive the equation for that, and the same equation is applicable for the system that is losing the mass. So we are going to consider a system that gains mass, let us say by absorbing particle. Okay. So let us say I have a mass m which is moving with velocity v, and I have another mass which is, let us say, delta m moving with velocity v naught. This is the situation at time t, let us call it the initial time, and at time t plus dt, if your v naught is larger than v, then they combined. So we have mass m plus delta m, and it moves with a velocity v plus delta v. Now here note that v naught is the velocity of the absorbed mass, or the small mass or a small particle, and v is the velocity of the system that gains mass, okay, or you can call it bigger mass. Okay. Now since all this thing happens in very small time dt, therefore we can use the impulse momentum relation. So let us use the impulse momentum relation. So it is following: if p1 is the initial momentum and the impulse is ftt, then the final momentum is p2. Now here p1, which is the initial momentum, is the moment of this particle and that particle. So we have mv plus delta m v naught. Okay. So this is the moment of the smaller and bigger particle initially, plus summation f external dt equal to final momentum is m plus delta m times v plus delta v. Okay. So let us expand it. So we have mv plus delta m v naught plus summation f external dt equal to mv plus m delta v plus delta mv plus delta m delta v. Now since delta m and delta v, they both are small, so therefore their product will also be small. So therefore this we can neglect, because this is second order in delta. So let us neglect this term. Now mv will get cancelled with this mv. So therefore I can write down summation f external dt plus delta m times v naught minus v equal to m delta v, or I can rewrite this as m dv by dt equal to f external plus dm by dt v naught minus v. So what I do is I divide it by delta t, and then those small delta I write down as d. Let us define this quantity v naught minus v as u relative. So, let us call u relative or rel equal to V naught minus V. Okay. Then this equation I can rewrite as m dV by dt equal to F external plus dm by dt into u rel. Okay. So, note that here u rel, the way we have defined it is V naught minus V, and V naught is the velocity of the small particle, of the absorbed particle, minus the velocity of the bigger particle. Okay. Now, let us say there are no external forces, for example, gravity etc. is not there. So, if there are no external force, in that case F external will be 0, and the same equation we can rewrite as m dV by dt equal to dm by dt into u relative. So, based on these concepts, now let us look at few problems. The first problem statement is following: at the instant of vertical launch, the rocket expels exhaust at the rate of 220 kg per second with an exhaust velocity of 820 meter per second. If the initial vertical acceleration is 6.80 meter per second square, calculate the total mass of the rocket and fuel at launch. So, clearly this is a variable mass problem. So, therefore, let us use this formula m dV by dt equal to F external plus dm by dt u relative. Let me choose that this is the plus y direction. Let us call it equation number 1. In the question we have been asked what is the total mass of the rocket and the fuel. So, therefore, m is something that we have to find out. The acceleration, the initial vertical acceleration is given. So, acceleration is dV by dt, it is given, it is 6.8 meter per second square. The F external, the external force will be mg and it is going to act downward. So, therefore, minus mg, which is minus m into 9.81, and dm by dt is the rate at which the mass is changing. It is given that it is 220 kg per second, and since the mass is decreasing, so therefore, it will be minus 220 kg per second. Now, what is u rel? U relative velocity, it was V naught minus V. V naught is the velocity of the small particle, herein it is exhaust and it is in the minus y direction. So, therefore, minus 820 minus V, initially the V is 0. So, therefore, this becomes minus 820 meter per second. Let us put everything in equation number 1. So, we have m into 6.8 equal to minus m into 9.81 plus 220 into 820. So, that gives m into 16.61 equal to 220 into 820, and that gives m equal to 10.86 into 10 to the power 3 kg. Now, let us look at another problem statement. A rocket of initial total mass m naught is fired vertically up from the north pole and accelerates until the fuel, which burns at a constant rate, is exhausted. The relative nozzle velocity of the exhaust gas has a constant value u, and the nozzle exhausts at atmospheric pressure throughout the flight. If the residual mass of the rocket structure and machinery is MB, when burnout occurs, determine the expression for the maximum velocity reached by the rocket. And it is given that neglect the atmospheric resistance and the variation of gravity with altitude. So, again here we can use the variable mass concept. So, for that we have the equation m dV by dt equal to F external plus dm by dt into u rel. Let us call it equation number 1. Now, here let us identify each and every term. So, we have F external, the external force is the gravity only, which is going to act downward. So, let me take this as positive y direction. So, minus mg will be the F external. Now, dm by dt, it is given that the fuel burns at a constant rate. So, therefore, it will be minus because it is burning constant rate, let us call it C or constant. Now, u rel is the relative velocity. So, the fuel velocity minus the velocity of the rocket, the fuel is going downward. So, minus u minus the velocity of the rocket, initially it is 0. So, that will be minus u. Let us put this in equation number 1. So, we have m dv by dt equal to minus mg plus c, which is constant, times u, and note that c is nothing but minus dm by dt. So, I can write down as dv by dt equal to minus g minus u by m dm by dt. Therefore, dv will be minus z dt minus u by m dm, and I can integrate it. So, v varies from 0 to v, let us say in time 0 to t, and during this time the mass changes from m naught to m. So, therefore, v becomes minus gt minus u ln m over m naught, or v becomes u ln m naught over m minus gt. Let us call it equation number 2. Now, let us find out this t in terms of the given parameter. It is already given that dm by dt is constant. So, let us use this equation, dm by dt equal to constant minus c. Let us integrate this. So, we have integral dm equal to minus c dt. Now, the mass initially it is m naught and later it becomes mb when the complete burnout happens, and let us say the time to complete burnout is tb. So, here as I said, tb is the time of the fuel burnout. Okay. So, we get mb minus m naught equal to minus c tb, or tb equal to m naught minus mb over c. Let us put it in equation number 2. So, this time gives the condition for maximum velocity, because that is when the complete burnout happens. So, let us put in 2. So, we have v equal to u ln m naught over m minus g m naught minus mb over c. Now, let us look at another problem statement. The end of a chain of length L and mass rho per unit length, which is piled on a platform is lifted vertically with a constant velocity v by a variable force P, find P as a function of the height x of the end above the platform. So, again this is also a variable mass problem. Therefore, let us use the equation m dv by dt equal to f external plus dm by dt into URL. Let us take this as positive x direction, and it is given that the chain is lifted vertically with a constant velocity v. So, it is given that v is constant, therefore, the acceleration which is dv by dt will be 0. Now, let us look at the F external force. So, F external is P, it will be plus P because it is acting in plus x direction, minus the weight of this chain, so which is mass times the g. So, mass is rho x into g, because rho is the mass per unit length, multiply by the length will give you the total mass. And since m is rho x, this is your m, therefore, dm by dt will be rho dx by dt, or it will be rho v, where v is the velocity with which we are lifting it. Now, let us look at u rel. So, u relative velocity, it is the velocity of the smaller mass. So, the smaller mass is kept on the ground, on the platform. So, therefore, this is 0 minus the velocity of the bigger mass, it is moving with a velocity v. So, therefore, minus v, 0 minus v. So, which is minus v. Now, put everything in equation number 1. So, we have m dv by dt is 0. So, therefore, 0 equal to p minus rho xg minus rho v into v. So, we have p is equal to rho gx plus v square. Now, let us look at another problem on the same concept. So, question number 4. The end of a pile of loose link chain of mass rho per unit length is being pulled horizontally along the surface by a constant force P. If the coefficient of kinetic friction between the chain and the surface is mu k, determine the acceleration A of the chain in terms of x and x dot. Okay. So, obviously, it is a variable mass problem. So, therefore, we can use m dv by dt equal to f external plus dm by dt into u rel. Let us call it equation number 1, and let us choose this as our positive x direction. So, in the question we have been asked to find out the acceleration A. So, that means dv by dt, something that is asked in the question. Now, the f external will be P, because P is acting in the plus x direction, minus the frictional force which is mu k times n, where n is the normal reaction force, and it will be equal to mg. So, it will be P minus mu k m into g. It is given that rho is the mass per unit length. So, therefore, m will be rho times x. So, therefore, F external will be P minus mu k rho x times g. Okay. So, as I said, m will be rho x, therefore, dm by dt will be rho x dot. Now, let us look at u rel, relative velocity. It is the velocity of the smaller mass minus the bigger mass. So, initially the smaller mass is kept into the rest. So, this is at rest, therefore, it will be 0 minus the velocity of the bigger mass, it is moving with velocity v. So, therefore, it will be minus x dot. let us put everything in equation number 1. So, we have m x double dot equal to p minus mu k rho x g minus rho x dot into x dot, and we know that m is rho x, therefore, x double dot will be p divided by rho x minus mu k g minus x dot square over x. Now, let us look at another problem, and the statement is following: fresh water issues from the two 30 mm diameter hole in the bucket with a velocity of 2.5 meter per second in the direction shown. Calculate the force P required to give the bucket an upward acceleration of 0.5 meter per second square from rest if it contains 20 kg of water at that time, and it is given that the empty bucket has a mass of 0.6 kg. So, again let us use the variable mass equation: mdv by dt equal to F external plus dm by dt into u relative. Let us call it equation number 1. Here m is given, m is the total mass, so which is 20 plus 0.6, because 20 kg is the water and 0.6 is the mass of the bucket. So, therefore, it will be 20.6 kg. dv by dt is also given, it accelerate with a velocity of 0.5 meter per second square. So, 0.5 meter per second square. Now, let us calculate F external. So, F external, so we have the situation, we have this bucket and then it is pulled by this rope, and the force is P. The same force is going to act over here. So, therefore, F external is P minus mg, where m is the mass of the water plus the bucket. So, it will be P minus m is 20.6 multiplied by z, which is 9.81. Now, let us look at dm by dt, the rate at which the mass is changing. It will be minus, because the water is coming out, density times the volume, and the volume is A into V, where A is the area, V is the velocity and rho is the density. Since there are two holes, so it will be minus 2 times the density is 1000 kg per meter cube multiplied by the area. Area is pi r square, where r is the radius. Here in the diameter is given. So, diameter is 30 mm. So, multiplied by 0.03 into 0.3 divided by 4 into the velocity. Velocity of the liquid is 2.5 meter per second. So, this comes out to be minus 3.53 kg per second. Now, let us calculate the V relative along the y direction. So, along the y direction, the velocity of the water is minus 2.5 sine 20 degree minus the velocity of the bigger mass, which is bucket here. Note that initially the bucket was at rest. So, it is given that it is rest. So, therefore, minus 0. Now, let us put everything in equation number 1. So, we have m, which is 20.6 into dV by dt, which is 0.5, equal to F external, which is P minus 20.6 into 9.81 plus dm by dt, which is minus 3.53 into V rel. So, which is 2.5 sine 20 degree, and this becomes plus. So, this gives you P equal to 209 Newton. With this, let me stop here. See you in the next class. Thank you.